from the foundations of quantum theory. But as you might see from the top of my slide, it says Quantinuum, which isn't a university. So I actually work for a quantum technologies company, or a quantum computing company called Quantinuum. And okay, these are the nice statistics that I'm supposed to present at the beginning of my slides. But basically, they're all over the world. They like build quantum computers and develop the software for them and the theory. And they work on other quantum technologies, including all of these things. And I am in the quantum cryptography part of this company. And you might be like, why am I telling you this? You don't care. But this topic that I'm going to present to you came up in the context of my research in quantum cryptography. So maybe it's a nice example of how you can have this sort of mutually beneficial relationship between technologies and like the foundations of physics. Okay. Okay, so what I wanted to present to you today is something that I basically just realized recently about basically a difference that you can observe if you describe the world by algebraic quantum field theory compared to if you describe the world by non-relativistic quantum theory. So maybe you're a person that is hoping that one day we'll be able to describe all the physics of our universe by algebraic quantum field theory, or maybe some modification or extension of that if you're slightly less optimistic. But if you were going to do that, something that you might hope is that when you then look at the domain of non-relativistic quantum theory, so your sort of slower experiments or non-relativistic ones, you might want the predictions to match up, right? So you might want that when you've restricted your view to the experiments that we know we can describe well with non-relativistic quantum theory, you might want to kind of reproduce the same predictions. But something that we already actually know is that there's a little bit of a spanner in those works. If you think about the phenomena of Bell non-locality. So something that we recently, well, not recently, I think in like 2020, found out about Bell non-locality is that if you take the broad general framework of algebraic quantum field theory and look at these experiments that study non-locality, then you see predictions that go beyond what is predicted by non-relativistic quantum theory. So if you're like only gonna impose on your world that it has to be described by this broad framework of algebraic quantum field theory, you have a bit of a difference between these two descriptions of the world. So this maybe leads you with like two possibilities or maybe more for how you want to view these differences. Oh, also, so I'll tell you a bit more about this difference in Bell non-locality, but the main thing I want to present to you is like another discrepancy of this kind, which is related, that I realized exists recently. So that will be like the main topic of the talk, but I'll explain these things more later. But given that there exists these two discrepancies, how are you going to kind of resolve that? So one possibility is that you are like diehard believing that non-relativistic quantum theory explains phenomena within its domain, like when things are not moving too fast, or these experiments that we've done, like many of these experiments that we've done, and we keep finding that like non-relativistic quantum theory is like working and making good predictions. So maybe you don't want to change that. So then these discrepancies, they're going to mean that should maybe shape the way that you study algebraic quantum field theory, such that you only look at the theories which reduce to giving the same predictions as non-relativistic quantum theory when you kind of take this non-relativistic limit, or however you want to view it. So that's all well and good, but maybe you actually are not that fond of non-relativistic quantum theory. It never did anything for you. Maybe you're not really friends. You don't work for a quantum computing company like I do. So then what would this mean for you? So then you would be opening the door to the possibility that you can describe the world by algebraic quantum field theories, which when you reduce them to these experiments where we're used to using non-relativistic quantum theory, you get some different predictions. So basically, all of my kind of people that are using non-relativistic quantum theory, because this is where I do my research in general. Also, if you have, that's why I'm more open to input on the AQFT part, because this is not something I generally work on, so please help me. What was I saying? But yeah, so then the other way around, you would be opening the door to basically non-relativistic quantum theory not being complete or not being correct. So then these are kind of two different interesting views you could take on this. So that's why I find the topic kind of interesting. Okay, so what is Bell non-locality? So this is a phenomenon that you see in experiments that we call Bell scenarios, which basically consist of two sub-experiments that happen in a space-like separated way. And these experiments are very simple. So you just have the first party, who we usually call Alice. She gives some input X, which is from some possible finite set of inputs. So the simplest case is where like X can just be 0 or 1. So she just gives a binary input, and then she observes some output. So also in the simplest case, this could be 0 or 1. And then the other space-like separated experiment is the same. So some party Bob gives an input, observes an output. And then if they repeat this many times, they can kind of infer what is the probability of seeing the output pair AB when they gave the input pair XY. And then they can find this probability for all the different AB and XY. And then we call that the correlation, which is going to describe the behavior of the experiment. So then if you're trying to describe the way you're doing your experiment by some theory or physical model, it will tell you which correlations are possible within that theory. And then the big deal about Bell non-locality was originally that the correlations that you could see in classical physics are represented by this square L. So they lay in some polytope. So this is the polytope of correlations that satisfy local realism. And then quantum theory gives you a bigger set of correlations than that. So you can go outside of this set into, for example, this circle that I've labeled CQS. I'll talk a little bit more about that later. But all of these correlations will satisfy something called the no signaling principle, which basically means that these two parties can't send signals or messages to each other faster than light because they're happening space-like separated. So all of these correlations are within some bigger set, which I've labeled NS for non-signaling. So when we're talking about non-relativistic quantum theory, this is what would give us this set that I've labeled CQS. So our experiment, we would say it's associated with a tensor product of two Hilbert spaces. And then the state of the system is just some vector, which is on this tensor product of Hilbert spaces. And then Alice's measurements are on the Hilbert space HA, and Bob's measurements are on the Hilbert space HB. So that overall, you get that your correlation can be described like this, which is basically just, yeah, Alice's measurements are on one side of the tensor product, Bob's are on the other, and then you're taking the sandwich with your state to get the probability of seeing A, B given X, Y. So this is what we do in my world when we're talking about these correlations. But what about if you wanted to do this with algebraic quantum field theory? So then you would have some C-star algebra A, where your observables were going to live. So they would be some self-adjoint elements of your C-star algebra. And because these two experiments are space-like separated, we're going to say that these two observables exist in commuting subalgebras of this bigger subalgebra. And then the state of the system is just some positive linear functional on the algebra. So then this gives us like a slightly different description of the correlations that we can see. So now we've got the probability of AB given xy is given by our state acting on these two observables which commute with each other because they're part of these two commuting subalgebras of the full algebra. Conveniently for people like me, you can use the GNS to phrase this all in the Hilbert space language. So basically, you can just say there's some joint Hilbert space HAB, which doesn't necessarily have this tensor product form. And then you can let Alice's and Bob's observables be anything as long as they commute with each other. And you get something that looks very similar to the non-relativistic quantum field theory, non-relativistic quantum theory case, but instead you don't have this tensor product in between anymore. You just have the commuting part imposed. Okay, so then this defines a set which we usually call CQC for like quantum commuting, QC. And what we found out in 2020 from this paper, which has this quite hard to understand title, MIP star equals RE. But a consequence of what they proved in that paper is that basically this set CQC is strictly bigger than the set CQS. So even if you take the closure of CQS, which is what I'm denoting here, then CQC is bigger than that set. So there are correlations that you can't even come close to approximating in the non-relativistic or the tensor product formalism that are possible in this sort of broad algebraic quantum field theory case. So this problem was open for quite a long time, and it was known as Tsirelson's problem. And it was kind of obvious that the inclusion goes one way, right? So maybe this is something that you can see easily. So in this case, you just need that the operators commute. So if you take the Hilbert space to be this tensor product Hilbert space, and then the operators to be the M's tensors the I's, the M tensor I's commute with the I tensor N's. So these are examples of some operators that commute. So basically everything that you can write in this form, you can write in the second form. So the inclusion goes one way, and then the part that was open is, does it go the other way? And then it turned out, no, no, it doesn't. So then you could say that AQFT is more Bell non-local than non-relativistic quantum theory, because you can get more of this resource, or however you want to phrase it, that's called non-locality. Oh yeah, which is pretty shocking, at least it was to me. Okay, but then a little bit of caveats, right? So here, I'm just using this like very broad framework of algebraic quantum field theory, where I'm saying that my spatially separated or space-like separated experiments, I'm only imposing that they have to be like associated with commuting subalgebras of the full algebra. So you could impose more structure on your AQFT framework. So for example, so if you impose what's known as like the split property, this basically means that you're reducing to like the tensor product case, and then the two sets become the same. So I think there's a nice paper by who's at the back about these ideas of operational independence and how you would phrase this in this framework. And also, from what I've heard, not that I'm somebody that works on these things, it's quite difficult to construct algebraic quantum field theories that sort of do useful things. So we don't actually know of any realizations of these correlations that are sort of outside of the tensor product set that are sort of in an AQFT. And these correlations are just difficult to characterize and describe anyway. So there's kind of a lot of work to be done there. So maybe this is like, yeah, there are a few caveats on this, but I still think it's like quite exciting that there is this potential difference. So what is the difference between these two formalisms? So if you naively look at it, it's basically the way that we describe space-like separation. So here we're like tensor product, and here we're just like they have to commute. So then you can ask yourself the question, like, can you see a difference between the predictions of these theories if you're doing some experiment that doesn't involve space-like separation on some level? So now I have some subtle foreshadowing. Yes. So that is the thing I want to tell you about today. That basically you get some analogous picture for what we call generalized contextuality in analogy to Bell non-locality on the other side. So then what is generalized contextuality? So usually to explain this, I use the group photo of like wherever I am, but you guys haven't had a group photo for a long time, it seems. So I've just sort of like expertly superimposed some of you onto this picture that has me and Jingyi in it anyway. I apologize if you're not on the picture, I was just like picking some people from the website. Okay, sorry, distraction. But so this is supposed to represent us and the world that we can interact with. And if you suspend your disbelief slightly and imagine that we are the kind of people that can perform experiments in a laboratory. So this part of the slide is like the operational world. So the things that we can do are, we have some preparation procedure for how we prepare our system in the lab. Which could just be like a list of instructions of what we do in the laboratory. And I'll call that preparation procedure P, for example. And then I also have some measurement procedure. So this is something that I can observe about the system by some other list of instructions of what I do in my laboratory, and I call that M. Then generalized non-contextuality is a statement about how this operational model relates to an ontological model that we could have to describe this theory of what's going on. So in an ontological model, we have that the system is always in some ontic state, which is usually called lambda. And then when I do this preparation procedure in my laboratory, I don't necessarily know what ontic state lambda I'm preparing, but all I know is some probability distribution over all the possible different ontic states lambda. So this is kind of like a hidden variable if you're familiar with that language. And then my measurement, then the probability of seeing some outcome A from my measurement M is just a function of what the ontic state of the system was. So this is why it's like an ontological model. So like my outcome probabilities only depend on this ontic state. So then if you want to find out the probability of getting this outcome A, given you measured M and prepared P, then you have to find out the probability that you're in some ontic state lambda, then multiply it by the probability of getting A, given that you're in lambda, and then either sum or integrate over all the different possible ontic states. Okay, so this is something you can do for quantum theory in what I've said so far. But then what you can't do is if you impose this requirement called non-contextuality about how the operational theory and the ontological theory relate to each other, you can't describe quantum theory if you do that. So what is this requirement? It's just saying if two things look the same to us on this level of things that we can observe, then they have to be the same also on the ontological level. So that means if I have two different preparation procedures, and no matter what measurement procedure I do afterwards, I always get the same statistics, whether I did preparation 1 or preparation 2. So I'll say that those two preparations are indiscernible. Then they have to be represented in the same way on the ontological level. So they'd have to be the same probability distribution over the ontic states. So basically, if it looks the same, it is the same. Like, this is also known as Leibniz's principle of indiscernibles, is like motivating this assumption. Maybe you think it's reasonable, maybe you think it's unreasonable. Whatever is the case, it's true that you can describe classical physics with such a model, a non-contextual ontological model, but you can't describe quantum physics or quantum theory in that way. So it's something that's sort of special or non-classical about quantum theory. Oh yeah, sorry. Also, there should be like transformations there as well as preparations and measurements, but it makes it a bit more complicated, so I always miss them out, and I feel sorry for them, poor guys. Okay. So now this looks very similar to the Bell non-locality slide, because we can think of analogous experiments where we can look at correlations and see differences between non-contextual theories and quantum. So in these scenarios, we just have a prepare and measure experiment. So we have a first input X, which decides how we prepare the system. And then we have a second input Y, which decides what measurement we do. And then we see some outcome B. So then now I'll call our probabilities Q. So this is the probability of seeing outcome B, given I made preparation X and performed measurement Y. And then we want to involve this idea of indiscernibility, or what we usually call operational equivalence, within the experiment. And we do that by saying that if I were to perform a mixture, like a probabilistic mixture of the two preparation procedures, say P1 and P2, I impose that I'm only allowed to use preparation procedures such that that mixture would be indiscernible from a mixture of doing P3 and P4. So this is just an example of a contextuality scenario, but and this is something that we call an operational equivalence. So like if you impose this on the states that you're allowed to use, then you see this difference between the correlations. So I'll give you an example, because maybe there's a bit of confusion. Okay, so like in quantum theory, your preparation procedure corresponds to a density operator, and then two density operators are equivalent if they're equal, basically. So then an example of 4 states that would satisfy this this equivalence that I wrote down for you here. So if you're familiar with like the block ball on like a 2-level system, if you had row 1 and row 2 as the eigenstates of sigma z, which we often call like the 0 and 1 states, and row 3 and row 4 as the eigenstates of sigma x, or the Pauli X operator, we often call the plus and minus states. Then if I take an equal mixture of 1 and 2, I get the identity over 2. But if I take an equal mixture of 3 and 4, I also get the identity over 2. So then this would be an example of 4 states that satisfy this equivalence. Okay, great. So I'll just go back. So generically in quantum theory, yeah, my preparation in non-relativistic quantum theory, my preparation will correspond to some density operator rho, which is on a Hilbert space. And then it satisfies whatever this equivalence is that I've imposed if these two density operators are equal to each other. And then I can describe, so the correlations that I can see in non-relativistic quantum theory will have this form, right? So the trace of like my measurement operator with my density operator rho x. And that was the example. Okay, and this example I gave you, I chose because if you choose some nice measurements, which kind of are diagonal in this block representation, then this gives you an extremal point of the quantum set, which is outside the non-contextual set. So this is some like non-classical example. Okay, but now if I wanted to do the same thing with algebraic quantum field theory, how would this be different? So it looks pretty similar, but now I have some C-star algebra and my states are positive linear functionals on those. And then if they satisfy the equivalence, similarly, I just have that like taking this mixture of these two is equal to taking this mixture of the other two. So it all looks quite similar. But what set am I going to get to? So I think to me, initially, it seemed like you would get to the same set because there is like no space-like separation and there's no like commuting tensor product difference, but it turns out no, right? In this case, you also get a bigger set. So for the example I gave you, this very simple example with the 4 preparations, if you just have 2 measurements and 2 outcomes, the 2 sets are actually the same. So these 2 formalisms would give you the same set of correlations. But more generically, if you allow yourself to have a greater number of preparations, or states which satisfy some equivalence, then you can see a difference between these 2 sets. This is like the main thing I wanted to point out in this talk. You also get a difference in correlations in contextuality scenarios. So, okay. So how long do I have?
You've spoken for about 25 minutes.
Okay, cool. So I'll tell you first a little bit about why, or how we can see that this is true. But maybe if you don't like math so much, maybe you won't like this too much. But then I'll go back to maybe like the consequences afterwards. So, okay. So something I worked on in the past is basically a map that goes between non-local correlations to these contextual correlations that I was telling you about. And this map works in such a way that the classical sets get mapped to each other. The non-relativistic quantum theory sets, which I've called Q and CQS, get mapped to each other. And then the bigger sets of non-signaling and the analog of non-signaling, which I didn't really explain to you, but just the analog of non-signaling, C, also get mapped to each other. But in this paper, we didn't look at the commuting correlations, and we sort of left this as something to look at later. And okay, so this map looks like what I've written up here. So basically, if you have some correlation, so now to make the notation a little bit easier, each one of the preparations, instead of just being labeled by X, it will be labeled by a pair, A and X, and it will become apparent why on the next slide. So yeah, I'll go to the next slide. So the way that this, so the intuition behind why this map works is that, so if this is our Bell scenario, so we've got this state shared between the 2 parties, but then imagine we're in some frame of reference where it looks like Alice does her measurement first. Then you can think of Alice's measurement as preparing Bob's system in some state. And the state that it gets prepared in is going to depend on the X that Alice chose and the A that she saw as the outcome. So we can call this state rho AX. And this is where this AX labeling is going to come in. Okay, quantum theory tells us how to describe this state rho AX. And then what you will see is that these states rho AX satisfy this equation here by the no signaling principle. So this is saying like the average state that gets prepared for Bob when Alice chose X is the same as the average state that gets prepared for Bob when Alice chose any other X prime, which is just no signaling, right? So Alice can't change Bob's average state by making a different choice of X, because if she could send a signal faster than light. But this equation is exactly in the form of these operational equivalences that I was explaining to you before, right? So basically, if you view the experiment in this way, we've got like the 3 ingredients for the contextuality scenario. We make some preparations, we do some measurements, and then there are some equivalences that hold between the preparations. So hooray, it's a contextuality scenario. Okay, and if you sub these things in where you should do, you will basically see that that if you view this Bell scenario as the prepare and measure scenario, the probability of getting B given the preparation A, X, Y, you can work it through, and it ends up being the probability of getting A, B given X, Y in the original Bell scenario but then divided by this marginal probability that Alice would get A, given that she measured X. And this is like the map and how the map works, right? So if you have some correlation on the contextual side that looks like this, it gets mapped to this correlation P of AB given XY, such that they like satisfy this relationship with each other. Okay, this was an example, but maybe it's not so useful. So this was kind of one direction, which was telling you if I start with something like a Bell scenario, it looks like a contextuality scenario. So that's showing me that my Bell correlations map to contextual ones, but then like the map is invertible, so it also goes the other way. So if I start with some contextuality scenario, which has like a quantum realization like this, so these states satisfy the equivalences that they're supposed to satisfy, then the question is, can I always realize this preparation part by having an extra system that's in an entangled state with my system, and then a measurement happens on it that prepares these states in the specific states that I want? And the answer is yes, conveniently. There's something called the Schrödinger GHW theorem. It has a lot of names because it's been rediscovered like many times by many different people. And this is basically exactly what this theorem says, right? So for any set of these states which satisfy this equality that I've given you at the top here, then there is a realization of this form that like prepares those states. So this is what we studied in this paper, and basically shows you that you can invertibly map between the set Q on the contextual side and the set CQS, the quantum spatial correlations, on the non-local side. But then, as I was saying, we didn't look at the quantum commuting correlations. So we know that if we start with quantum commuting correlations, we will map to some set which is bigger than Q because of like the invertibility of this map. But we don't like have a priori have some interpretation of what this set is. But then I was reading this paper at some point, which is called A Bound on the Quantum Value of All Compiled Non-Local Games. So you don't need to know what a compiled non-local game is. But at the end of the abstract, they say it further relies on a sequential characterization of the quantum commuting operator correlations, which may be of independent interest. So yes, I am the independent interest. Probably other people as well, but certainly me. So yes, basically what the result shows is what I've been telling you. So now, like if you apply our map to this bigger set of quantum commuting correlations, you'll be taken to this set here, and this will be exactly the set of correlations that you get from algebraic quantum field theory. And then because we know that this set like strictly contains this one, then we find that this set strictly contains this one. So you also get this gap in between, and this is how we get the result. Okay, so this was just one direction, but maybe it's not so interesting. But I find the one of the directions quite interesting, which is if you have the quantum contextual correlation with some C-star algebra description of that correlation, then how do you construct the Bell one? And it basically comes immediately out of what's called the Radon-Nikodym theorem. And this is basically telling you if you have two positive linear functionals and one is an upper bound for the other one, which basically means if I do this one minus this one, I get something that's also positive. Then I can describe the action of the smaller one basically using the GNS representation of the bigger one, along with some extra operator. So when I have my smaller positive linear functional acting on some element of my C-star algebra, I can write that. So if this T wasn't here, then this would be the bigger one acting on A, right? This is what like the GNS tells you. So you have this map that takes you from your C-star algebra into your bounded operators on this Hilbert space. But now for the smaller one, I just have to add in this operator T here, and this operator will commute with the image of A on my bounded operators of the Hilbert space. So this T is always going to commute with whatever this operator here is, and this T will be between 0 and the identity. So then this is actually basically exactly what we want. So in our problem, we have these positive linear functionals, and if I like mix them together in a certain way, they are equal to some other positive linear functional, which means that this one that they sum to is going to be an upper bound for each one of them. Because if I do this one that they sum to minus any other one of them, I'm still getting something positive, which is like what I told you was the definition of one being bigger than the other. So now so if I just call like my probability multiplied by my functional phi tilde, they satisfy this relationship that they needed to satisfy in the theorem. And this basically gives me the result that I want. So I had that my probability of seeing B, given that I prepared AX and measured Y, was given by this formula, like my functional acting on my measurement operator, BYBs. So if I write that now in terms of this tilde one, so I just divide by this PAX probability, then I can apply my theorem to this part of the expression here. So now my T operator is this MXA operator. So there'll be one of these T operators for each one of these functionals, the MXA. And we know that MXA, because it's in the commutant here, then this is going to commute with whatever this operator is. So then if I just call this operator NYB, then this is what I was trying to show, basically, that I can always express this in this form with these two operators that commute with one another. And thought that was quite nice. Okay, yay. Okay, so you've indulged me in like the details of how this works. So what are the consequences? So there was this nice paper that came out a couple of years ago now, which basically ran through in the non-local case, what are the possibilities for the non-local correlations that we might be able to see in nature. So they're basically saying, one possibility is that you can never see any of these correlations P, which are in the commuting set, but not in the like quantum spatial set. And okay, so then they talk about some different possibilities. So for example, maybe you can see them for like spatially separated experiments, but not space-like separated experiments, or so on, until like the other extreme case, which is like basically you can, there exist experiments where we can like see all of these correlations that are outside. And for our contextual case, okay, so I've just written two options. Basically, there's some physical realization for these extra correlations, or there is not. But the point I wanted to point out is I think that like, no matter which one of these turns out to be true on the non-local case, I think it's still possible that you can have a physical realization in the contextual case. So even if it turns out that you find some algebraic quantum field theory that you're happy with for describing things, and it rules out these extra correlations in the Bell scenario setting, the non-local setting, you still might be able to see these correlations in the contextual setting. Yeah, and that's just what I'm trying to say here. So, maybe this point has a physical realization, even if this point on the non-local side doesn't. Yes. Yeah, so there's like a lot of open questions. I think some of them are very difficult. For example, these questions of like, can we actually physically realize these correlations either in the non-local case or the contextual case? Very difficult. Maybe slightly less difficult, but also still quite hard is, so I described to you a specific kind of contextuality scenario where you have these equivalences between the, the preparations, but there are many other kinds of contextuality scenario. And then you can ask the question, is there this gap between the algebraic quantum field theory set and the non-relativistic quantum theory set, like in more scenarios? And these other questions, okay, they're kind of things that I haven't really told you about in this talk, but basically just trying to demonstrate that quite a lot has been studied about non-locality, slightly less so about generalized contextuality. So, you know, there are some like reasonable problems that you can study, and you might want to consider, you know, there might be some more tractable options within contextuality compared to non-locality. And that's the end of the talk. Thanks for listening.